is only following the ideal equation in the middle region during the flow bias. Right, where your bias is not too small, not too high. And then for the reverse bias, it's only valid in this initial region. Right, where your generation current is not too high. So I'm just to tell you, reality is always very different from ideal case. And usually what happens is that the ideal case is made under very many assumptions. These assumptions can be broken depending on the real situation, right? So always keep in mind that the equation that you learn in the textbook is not always true. Okay? Now we need to move on to another topic, right? So here is the metal semiconductor contact, which is extremely important, right? Do you know why it is important? Because all the semiconductor device always need electrodes, right? For example, if you have an N-type silicon and you need to deposit some metal contact on the surface, right? You have two choices. You can choose gold or aluminum. Do you know these two metals will make a different IV curve? And you measure the IV curve by applying the voltage. And you will see two results. This is the IV curve. Voltage currents. One metal will give you this, the blue line. And the other metal will give you the green line. Okay? Do you know which metal give you which line? Because the metal make a big difference. If you choose the wrong one, you will destroy the device. Metal is very important. Don't choose the wrong one. For N-type, if you want to make the green line, you need to choose which one? Let me think about it. You choose aluminum. And if you choose gold, you will have the blue line. Aluminum give you the green line. Gold give you the blue. Okay. Why? Because different metal will give you different resistance at the interface. Okay? Because the interface is made by two totally different material. One is pure conductor, which is metal. One is semiconductor, which is not metal. So usually the two different material and then connected to each other, the interface is a bigger issue. So the contact resistance make a lot of difference, right? So here we can show you the examples. Maybe I can show you another figure. If you look at the untyped situation, okay? You know the untyped semiconductor by looking at the Fermi level in the Venn diagram, right? So for untyped semiconductor, you see the Fermi level is in the upside, right? Closer to the conduction band, right? So on the figures on the right hand side, you see two figures. Two different metals. Before contact the untyped semiconductor. So the semiconductor is the same, all of them are untyped. But the metal is different. What's the difference? One is of large work function. One is of small work function. So work function is the distance between Fermi level and the vacuum level. Okay? So that's the difference. We define it as a work function, 波函数. Okay? So here I show you work function make a huge difference. Right? Work function is the energy difference between the Fermi level of the metal and the vacuum level. So what do you mean by Fermi level? What do you mean by vacuum level? 什么是真空冷淡? So the energy level is on the top. The topmost energy level is the vacuum level. Okay? So you can see the definition of a Fermi level. Okay? No, definition of a vacuum level, right? And I can make it up. Vacuum level, yeah. The energy level of the electrons that is free from any material. Okay? The energy level of the electron that is free from any material. So we call it a vacuum. Where is the vacuum? Vacuum means outer space, 外太空. Because there is no air, no gas in the space, so we call it a vacuum. So if your electron is in the vacuum environment, that means the electron is really free from any influence from the material. Right? So when the electron is excited to the vacuum level, that means this electron is no longer belong to the material. It is too far away, and it is not controlled, influenced by this material. So it is the level or the minimum level you need to move the electron away from this material. That is the definition of a vacuum level, right? So now, make sure you understand the definition of a work function. Okay? Work function, which is the difference of energy between the Fermi level and the vacuum level. Okay? So you have a Fermi level in the metal, you also have a Fermi level in the semiconductor, right? Which means you have the work function for the metal and the work function for the semiconductor. Okay. So usually the work function of a semiconductor is not a constant. It is not a constant. See? That's the work function of the semiconductor, because for a semiconductor, your Fermi level sometimes can be high, sometimes can be low, depending on the doping, right? If you have a type of doping, your Fermi level is high, which will make the work function small, because that's the difference between the Fermi level and the vacuum level, right? If your work function is for p-type, where you have the Fermi level closer to the valence band, so the work function for p-type semiconductor is usually large than the work function of n-type. So which means the work function for semiconductor is never a constant, because it depends on the doping. But the work function for the metal is a fixed value. It's like a band gap of a semiconductor. You can look it up by Google or by some textbook, because it is a constant number as long as you know the name of the metal, right? So here we see, if you choose the same n-type semiconductor, same doping, but you choose two different metal to make the contact. For example, you have aluminum and gold. Aluminum is of the work function small. Okay, so this is the situation for the aluminum, where you have a small work function. And for the gold, usually the work function is larger, corresponding to the top one, right? So we can see work function will change the interface band diagrams after they are in contact of each other. So for the aluminum, where you have a smaller work function, your semiconductor is bending down when you make the contact. This is before contact, which means the metal and the semiconductor are far away from each other. They are not contact. But if you brought it together, make the deposition of metal on the surface of the p-type, n-type semiconductor, you will have two different situations depending on the work function. For the small work function, your bands going down. For the large work function, your bands going up. That's the key difference. Right? So which one will give you large currents? Bending down or bending up when you apply the voltage across the interface? Make a guess. Right? Imagine you are an electron. Right? That's always my suggestion. If you don't know the answer of the question, you imagine yourself as an electron and see what you will do in this situation, right? So you have two situations to choose. One is the situation in the bottom, one is the situation on the top. If you are injecting currents from the metal to the semiconductor, from the metal to the semiconductor, right? Will you have a large current here or large current there? Which one will give you larger currents? I hope you can make the right choice. 所以同样的半导体，不同的金属，一个是产生这种界面的能带，一个是产生上面的界面的能带，一个是往上弯曲的能带，一个是往下弯曲的能带。半导体的能带，金属能带不会弯曲，因为金属没有 conduction band， 没有 valence band， you have zero band gap for the metal, so you don't see conduction band, valence band. You only see the conduction band and a valence band for the semiconductor. No band gap for the metal, right? So which one will give you larger currents? top one 的 bottom one， 猜一下，往上弯的能带会有比较大的电流，还是往下弯的能带会有比较大的电流？杨轩，你在不在？陈思祥在不在？一半的人不在哦。陈子柔在不在？刚好都觉得他不在了。简伟哲在不在？OK。我的问题是 ，Which one will give you higher currents? This one or that one？ 哪一个会产生比较大的电流？好，假设你把它镀在一个很太薄的 silicon 上面，这样子的能带会有比较大的电流，还是那样的能带会有比较大的电流？对不对？当我把电流或是电子从金属灌到半导体里面的时候，你觉得哪个会产生比较大的电流？上面来，下面来，大电流。为什么？下面的电流会比较大。你 say this one will give you larger currents. Why? This is supposed to be easy, right? If you can understand what happens to the electron when they are going from here to here, what happens? 那电子要从金属那一边灌到半导体那一边，为什么这样子的电流会比较大？电流就是从金属灌到半导体电流，电子的流动或者电子的流动，对不对？为什么？Simple reason. Yes. You see which energy barrier is higher? 你看哪一个能占比较大，哪一个能占比较小嘛，对不对？就像电子要爬山一样啊。当电子从金属要灌到半导体的时候，它要爬的山哪里比较高？上面那个山比较高，还是下面那个山？下面这个山比较高还是比较低？ Mountain, like an energy barrier. The energy barrier in this bottom diagram is smaller, right? How do you mean by energy barrier? Energy barrier is the difference between this point and this point, 对不对？所以我们说能阶障碍指的就是电子行进的路径，电子只能在 conduction band 上面跑而已啊 ，right? The electron can only move in the region above conduction band, because electron below the conduction band edge not movable, right? For the metal, electron is moved above the electron, right? So you can imagine if there is an electron injected from the metal side and move it into the semiconductor side. The energy barrier is the energy difference between this point and this point, which is small compared to the situation on the top, where you can see when your semiconductor band is going up, you are increased the potential barrier or energy barrier for the electron ejected from the metal, 对不对？所以当我的能带往上弯的时候，你在增加电子移动的障碍。Right? So when you are making the bands, the conduction band and the valence band going up or bending up, you are increasing the energy barrier for the electron from the metal to the conduction band. So when you have a large energy barrier, you are making this blue line. Okay? So this blue line we call it Schottky. Okay, so you see the current is almost zero. When your bias is small, it's like the p-n junction, right? Why? Because when your bias is small, the electron or the energy is not enough to overcome the potential barrier at the interface between metal and the semiconductor. But if you make the bending going down, you can easily make this green line, which is the ohmic contact. That's why work function make a big difference. Right? Because work function is the key factor, key parameter determining whether this bending is going down, going up. Okay, if you choose the work function smaller, like aluminum, you will make the bending going down, reducing the potential barrier for the electron to move from metal to the semiconductor. If we choose gold, which has a large work function, you are making the bends going up. And then when you inject current from the metal to the semiconductor, you are impeding the electrons or the currents moving from the metal to the semiconductor, because the electron will see higher potential barrier, which will stop them if your bias is not high enough. Right? Can you agree? Do you agree with me? 合理吗？好，所以这种能接的电流就会比较大，上面那种能接的电流就会比较小，因为它电子都挡住了，对不对？好，因为 N type 的半导体来讲都是电子在产生电流的，因为电子有多有电动，对不对？好，所以 N type semiconductor we only consider the transportation of electrons. If you agree the results of these two band diagrams, now here comes the even more important question. Why is going down? Why is going up? 为什么? How do you know if the bands are going down or going up? By knowing the whole function here. You have 50% to make it right if you do it by purely guess. But you can make it 100% right if you know the simple rule. Okay, what is the simple rule? 我的问题就是，那为什么这边是往下弯，那边是往上弯？对，为什么握方旋小的就会有往下弯的能带，握方旋大的就会往上弯的能带 ？It's not always the case. If you change the domain type from N to P, the result is just the opposite. So you cannot just memorize, oh, large work function make the band going up, small work function make the band going down. It's not a rule to memorize. It will confuse you. Let me show you the example for P-type. See, for the P-type situation where you have the Fermi label in the bottom, close to the valence band, right? And then you connect to the large Fermi level, large work function. You get the opposite result. You see the band is going up. Right? And for the work function smaller, you make the band going down. So that one is ohmic contact for small work function. Sorry, just a change. That one is for Schottky barrier. This is for ohmic contact, right? Because remember, for P-type semiconductor, it is the hole traveling inside the valence band So you need to imagine yourself as a hole instead of electron. When you are a hole, you are moving in this region. So this is an open contact for the p-type of semiconductor. This is the Schottky contact for the p-type of semiconductor. So if you don't know the basic rule, it is so confusing. You cannot just make the memorization say, oh, large Wall function will give you Schottky, and the small Wall function will give you Omi, which is wrong. Right? Because it changes if you have a different doping pipe. Right? So what is the basic rule? Basic rule to me is common sense. You will never forget common sense. What is common sense? 常识。什么叫常识 ？Common sense. The particle, no matter it is electron or hole, is always moving from high energy level to the low energy level. 这个叫做 common sense， 水往低处流，会不会很滑稽 ？You will never forget. Water is always flowing from mountain to ocean. Water will never flow from ocean to the mountain. Never. Why? Because the mountain is high, ocean is low. Right? Electrons, holes are like water. They always moving from the higher point to the lower points. So you need to know whether you are electrons, whether you are holes. If you are electron, you move from the high point to the low point. If you are holes, same. You also move from the high point to the low point. Right? So again, let me remind you, when you are drawing the band diagram, what is the vertical axis? This is the 100 times I asked the same question. 第100次问的，对不对？当你在画能带图的时候，纵轴是什么？好吗？纵轴，纵轴是能量，谁的能量？电子的能量 ，right? The vertical axis is the energy of electron, right? So if you are imagine yourself an electron, you need to remember this is high energy, this is low energy, because this is high, this is low. But if you are a hole, the bottom is the high energy region, the top one is the low energy. So because you are the hole is the opposite definition of energy, up and down. Okay? So for electron, this is the Fermi level here. I told you before, right? Fermi level is like a water level, right? So electron here has a lower water level of lower Fermi level. Electron here on the main semiconductor side is also is of higher energy level. So when you make this in contact, where will the electron flow? 这边的水位高，这边的水位低，连通管原理 假设两个水桶的水不一样，因为它的 two buckets, one is of higher water level, you have another one with lower water level. When you make these two buckets connected together, what will change? The water will flow from here to there, right? Until what happened? Until the level of the two sides or level in the two buckets enter the same height, then the water will start flowing, right? 就像水流一样，连桶管原理，不管你的桶是大桶是小啊，反正水位高的那一桶，当它接到水位低的那一桶，高水位的一定是慢慢往下降，低水位的一定是慢慢往上升啊，因为水的能量就是从高的往低的流嘛，对不对？ Same thing for the electron. When the electron is of high energy on one side, low energy on the other side, it will not stay in equilibrium until the two levels are at the same height. Right? That is the definition of thermal equilibrium. Right? So when you brought these two materials together, you are making the Fermi level going down and then making the Fermi level going up. Right? But remember, this is a special case. What do you mean special case? Special case is this is metal, this is a semiconductor, which have a huge difference in electron concentration. Which one has much more electron? Metal or semiconductor? Metal. So imagine if you have a lake in a mountain, and there is a waterfall making the river connecting the lake in the mountain on top, and ocean in the bottom side. So when all of the water inside the lake up in the mountain become empty because all the water flowing to the ocean, will you see the water level of ocean change? Yes or no? 知道我的问题吗？当我有一个高山湖泊，里面的水全部都流到海洋里面的时候，你的海平面会不会上升？会还是不会？海平面的水超级多，高山的湖超级少，所以当湖水都流干的时候，海平面会不会上升？ Yes or no？ 那会不会？不会。就算上升，你也假设没有上升，因为你看不到。Right? The change of the water level in the ocean is so small, you can ignore it, right? Because you have so much water in the ocean compared to the water in the lake. Electron concentration in the semiconductor is like the water in the lake. Electron of the semiconductor, electron of the metal is like the water in the ocean. It's a huge difference. So when you brought these two materials together, this Fermi level will not change because it's just too much electrons, too many electrons. So the water level or the Fermi level will gradually go down until it reaches the same level. How do you make the Fermi level go down? 你怎么让 semiconductor 的 Fermi level 下降？How do you make the Fermi level go down? See, this is higher, this is lower, right? By flowing electron from here to here. So you can see the distance from the Fermi level to the conduction band become longer, which is telling you electron in this region, close to the interface, become less with the go to the size of a metal, right? Because of the energy difference, because of the level difference. Electron is like water. It like to go from the high place to the low place. When they finish the traveling, electron concentration will become less because they all move to the metal side due to the energy difference. However, for the electron deeper inside the semiconductor distance between the Fermi level and the conduction band. No change, which is the same as the distance between the Fermi level and the conduction band before they contact. So these two band diagram is to show you when you are making the metal contact on the semiconductor surface, you only change the carrier concentration in the top layer. Few thickness, only electron in the very thin region will change, but in the bulk region, no change. Okay? How do you know it? You know it by looking at the distance between Fermi level and conduction band. Right? Because you know N equals Ni, not Ni, I can use another way, equals Nc times exponential 10 Kp, we have minus Ec minus Ef, right? So you can see distance between the conduction band and the Fermi level. Conduction band and the Fermi level is determining the electron concentration. Right? So always pay attention to the distance between Fermi level and the conduction band. You have a longer distance because the band is going up. So which means you are reducing the electron concentration in the region close to the surface. And deeper in the bulk semiconductor, because it is far away from the metal, no change. Okay? Common sense. Makes sense, right? Electron like to go from the high point to the low point. So for the situation on the top, you just see the opposite situation, where you have a higher electron level on the metal side, low electron level or low Fermi level on the semiconductor side. So when you are connecting them together, you move the Fermi level on the semiconductor side up and up until you reach the same level as the metal, right? So after the thermal equilibrium is reached, which means the Fermi level is aligned, they are in the same height. That means we have reached the thermal equilibrium. Then you can see the electron concentration is changed because the band is going down. Why? Because it receives more electrons from the metal, making the electron concentration in the surface region higher than before, right? So you can see the energy distance between the Fermi level, the blue line, is closer to the conduction band because conduction band is moving down, making it closer to the Fermi level, right? So you can see in that case, you have a higher electron concentration at the interface, low electron concentration in the bulk region. Why? Because your Fermi level is higher than the Fermi level in the semiconductor. So when you move them together, electrons is going from the metal side to the semiconductor side, making the concentration going up in the semiconductor interface. Right? So if you can understand this and this, it's much easier for you to check the untapped region. Right? The only difference you see is the position of the Fermi level. But untapped is up, closer to the conduction band. But still you have two situations. One is metal high, one is metal low. Okay? High means higher than the semiconductor, low means lower than the semiconductor. But for example, in this situation, you are making the electron moving from metal to the semiconductor because the Fermi level is higher than this side, right? So when you see the electron coming from here to here, this electron concentration will go up. How do you make the electron go up by drawing the back diagram? You need to make the back go down, making the conduction back closer to the Fermi level, right? So the key information for you to determine whether the band should go down or go up is by determine the direction of the electron traveling. Okay, if you are clear about the direction of electron traveling, either from metal to semiconductor or from semiconductor to metal, only two choices. This direction or that direction by common sense. Because as long as you know electron always going from the high point to the low point, you will know the right direction of the electron flow. And then once you know the right direction of electron flow, then the next one is to determine whether you have a more electron or less electron. If you have a more electron, your band should go down, making the conduction band closer to the Fermi level. If you have a less electron, making the band going up, because you are losing electron from the semiconductor to the metal. So this common sense is for you to know bending down or bending up. That's the key. Because bending down is making OB contact for N-type. Bending up is making Schottky contact for the N-type, right? For the P-type, bending down is making Schottky. Bending up is making ohmic, right? So ohmic and Schottky is see, are you increasing or decreasing the potential difference for electron and holes? So here we have so many combinations, right? You can have an N-type, you can have P-type. You can have a large work function. You can have a small function. And then I will add more combination. You can have a reverse bias. You can have a forward bias. Right? It's all from the common sense. Okay? So, for this metal semiconductor interface, make sure you understand, you know the definition of 4 key parameters. 3, work function. What's the work function? Energy difference between the Fermi level and the vacuum level. What is the definition of vacuum level? Be clear about it. Right? That's the energy level. Meaning the energy level that is making the electron free from any material. What's the electron affinity? I haven't mentioned this, but it's already shown here. Electron affinity C is this guy, which is the distance of energy distance between the conduction band H to the vacuum level. That is called affinity. 电子亲和力. You need to know this in order to calculate a very important parameters. What is that? Schottky barrier. Right? So for example, N-type Schottky barrier is equivalent to work function minus affinity. Why do you need to know this parameter? Because this Schottky barrier is the key to determine the turn-on voltage here by Schottky barrier. Right? If you have a large Schottky barrier, this turn-on voltage will become large. If you have a small Schottky barrier, this turn-on voltage will become small. Right? Because this is the potential barrier impeding, blocking, stopping the electron flow from the metal to the semiconductor. So you got to know how to calculate the Schottky barrier for N-type, which is easier. Also, you need to know the Schottky barrier for P-type. Here. Alright, so what's the Schottky barrier for the P-type? It's not said in the textbook, but I give you the answer in my handwritten class notes. Here. See, that is the equation for the Schottky barrier for P-type semiconductor, which is a little bit difficult, more difficult than the N-type semiconductor. Make sure you know how to calculate this by knowing the 4 parameters, which is 4: vacuum level, Wall function, electron affinity, Schottky barrier. You will see this again in the final. Because to me this is very important. If you want to work as a semiconductor engineer, you need to have the knowledge, expertise, knowing which metal to choose in order to achieve ohmic or Schottky contact. If you choose the wrong metal, you will make your boss angry, right? Because let me ask you, most of the semiconductor like ohmic contact or Schottky contact. If you want to save power, if you want to save energy, you like this green line or this blue line. Green line is ohmic contact. Blue line is Schottky contact. For most of the semiconductor device, which one can save the energy? Now, which one? Huh? Which one? Schottky. Wrong. You have a very small current for Schottky contact, which means you need to apply higher voltage in order to turn on the device. Higher voltage means higher energy consumption. Not good, right? So most of the semiconductor, they need an ohmic contact. And they don't want any potential barrier between the metal and the semiconductor, unless you have a very special purpose. If we just increase, if we just maximize the current injected from the metal, make sure you choose the right metal, making the ohmic contact, right? Because the condition for N-type and P-type to make ohmic contact is different. For P-type semiconductor, you need to choose a metal with large Wall function. Large Wall function metal make ohmic for P-type. Small Wall function make ohmic for N-type. Okay, but that's not the rule to memorize because it is so easy to get confused. That's the one to know. Okay, please. Electron, like a water, always like to travel from the high points to the low points. High points means high energy level. Low points means low energy level. Okay, that's it. It's everything I want to tell you about the p-n junction. No more. Okay, of course, once you know the Venn diagram, make sure you know the bias condition where you have a split Fermi level. One is high, one is low. Okay, that's the same results for the p-n junction. Next week, we will move on to the transistor, which is important. See you there. Thank you.